Hey Precalc, this is going to be factoring day 2. You can see the title given right here. It's going to be all about perfect cubes today, which is a technique you learned about in Algebra 2. I'll give you a second to maybe locate some paper that you're going to want to take some notes on as far as the patterns are concerned for perfect cubes. And like I was saying in the last video, I think a lot of the next few days might have the potential for you to be taking some notes on your own. So you want to make sure that you have a fair amount of loose leaf mixed in to your binders with all the note packets that you'll be getting. So as far as perfect cubes are concerned, before we jump into what that factoring technique looks like, I actually have some multiplying practice for us, because I think once we start multiplying these polynomials together, we'll start recognizing some of the patterns that are associated with perfect cubes. So what I'll tell you about these videos in general, and this will probably be for the majority of the school year, is that I will most likely move faster than I would if this was happening in class. The reason being is that nobody's stopping me and saying, hey, wait, Mr. All, you're going too fast, or hey, wait, I have a question. So you might naturally find yourself, as you're working through these questions, you might find that you have to hit pause every now and then, and I'm just going to leave that up to you, that you guys can handle that. If there are issues with the videos and you have questions, you'll reach out to me and let me know through email or otherwise. So to multiply these polynomials, I have nothing against you doing some box method work here. Just to save myself some space, I don't really have a lot of room to show the box method multiplication. Since you're writing them in your notes, you would have plenty of space to do that. So I'm just going to actually distribute the x to all of these terms and then distribute the -3 and see what happens when I combine some like terms. So that's going to leave me with x cubed, first and foremost. And then I'm going to get a plus 3x squared plus 9x. And then when I distribute the -3 throughout, I get minus 3x squared minus 9x minus 27. So that's what the factorization looks like. Here's what that product looks like, I should say, when you multiply that out. So now I want to combine like terms, and we'll see that 3x squared and -3x squared cancel out, 9x and -9x cancel out. So the resulting product here is x cubed minus 27. Okay, moving on to the next one, same thing. Do some quick product here, see what you can get when you multiply the binomial times the trinomial. So I'm getting that the first term would be 27x cubed plus 18x squared plus 12x. Take that -2, distribute it, so we get minus 18x squared minus 12x, and then at the end, minus 8. So similar to what we had in number 1 here, there are a bunch of things that cancel out, the 18x squareds, the 12x's, and I'm left with 27x cubed minus 8. And it's probably not a big surprise at this point that the terms that we're left with in each of these scenarios are both perfect cubes. X cubed is certainly a perfect cube. X times x times x. 27 is a perfect cube because it's 3 times 3 times 3. 8 is a perfect cube because it's 2 times 2 times 2. So that's what we're really heading towards here, is actually what's the pattern for taking this and making it look like what we started with, because what we're starting with in each of these cases is a factored expression. Okay, last case, number 3 here. Why don't you try that on your own? Hit pause quick, see if you can get the correct product when you multiply those together. When you hit play, you'll see the correct answer. So I'm not going to show the multiplication steps here, but this should come out to be b to the 3rd, or b cubed minus 8x cubed. So if you got that from the practice, perfect. But what I want to do is, again, kind of bring this pattern together and say, how could I have taken this and made it look like this expanded factored form here? That's the goal. So moving on from here, before we even do that, I want you to take a minute and think of some perfect cubes that you know. We've already talked about some of them, like 8 and 27, but see if you can make a list that almost goes in order from the smallest perfect cube to the biggest one you can list. And I would say if you need a calculator to assist you, there's no issue with that. But hit pause for a second, make that list. I'm going to create the list right now. So if I start with the smallest perfect cube, it should be 1, because 1 to the 3rd is 1. And then 2 to the 3rd would be 8, and 3 cubed should be 27. So those are the first 3 you should have listed. You move on from there, 4 cubed is 64. 5 cubed is 125. And those are the ones I would say you should be most familiar with without necessarily always relying on the calculator to determine that. These are the most common that you'll see come up in factoring with cubes. But if we go a little bit further, 6 cubed would be 216, 7 cubed, 343, 8 cubed, 512. We're now getting maybe into some unfamiliar territory with some of these values. 9 cubed would be 729. And then finally, 10 cubed, you should be familiar with that one. That one's 1,000. So knowing the first 10, I would say without maybe, again, always having to check on that calculator, not a bad idea. But I would say the first 5 are the ones that come up most commonly. So let's talk about that general rule for factoring with cubes then. I'm going to break down this pattern for you as to how you'll develop it with given scenarios, different given expressions. But here's the general rule. It's x to the third minus y to the third would have this factorization. So it's always going to be a binomial times a trinomial, like we saw in the multiplying practice. And it's going to be x minus y in this scenario times x squared plus xy plus y squared. So this is the general rule specifically for the difference of perfect cubes. If you didn't quite get that, if I went too fast up here, we're looking at the pattern if we're taking the difference of perfect cubes. Okay. So let's go ahead and break down this idea a little bit further and talk about how do we develop what's in each set of parentheses. So looking at that general rule again, this is already in your notes. How do we get the first set of parentheses? It winds up being the cube root of each of these terms. So not the square root, because it's not perfect squares, but if we think about the cube root, what multiplies by itself 3 times to get these quantities, that's what's going to go in the first set of parentheses. And notice how that subtraction sign stays if it was difference. The second set gets a little bit more complicated. So here are the 3 things that happen in the second set of parentheses. You're going to look back at the first set of parentheses. Look at this binomial first. And then you're going to square the first term. So notice how x got squared. In the middle, you multiply. And that kind of M and M go together, right? Middle, multiply, middle, multiply. So what did I do to get the middle term? You multiply x and y. You're multiplying these terms together to get what's in the middle. And finally, at the end, you square the second term. So the second term that I'm referencing is this y right here. Square the second term of the binomial to get y squared. I did make a note to notice the signs in the second set of parentheses. They will always be plus plus, always. So take a second to get this in your notes. I think it can be useful if you get stuck at some point. You're like, oh man, how do I get what's in the middle? If you have this written down as far as the steps go, I think it will be useful for you to go back and get some practice. Hopefully it actually looks and sounds a little familiar from your days of Algebra 2 last year. So here's our first practice question, y to the third minus 1. You know, we've already established that something cubed is definitely going to be a perfect cube. And then beyond that, we might have other values like 1 and 8 and 27. Those are going to be ones that commonly come up. So 1 is also a perfect cube. To factor this, the first thing you would do is you would list the binomial y minus 1. Okay, so y and 1 are the cube root, respectively, of y cubed and 1 up here. So how do I do the trinomial that follows? I have to square the first term. The first term is y. So the first term in the trinomial should be y squared. Then I'm going to multiply the terms to get the middle. Y times 1 is just y. It's always going to be a plus there. And then at the end, you're going to square the second term. So at the end, you'll have plus 1. The second term I'm talking about is the 1 right here. So that would be the factorization for y to the third minus 1. Let's move on and talk about some additional practice problems. So here's 3 others. Take a second, hit pause if you need to copy those down into your notes. But we're going to go ahead and factor these. So we're going to start with 27x to the third minus y to the third. So we know that 27 is definitely one of those perfect cubes. So the binomial would be the cube root of each of these. It would be 3x minus y to start. The only thing you really have to be cautious about is that the next thing you're going to do is you're going to square that 3x. So when you square that 3x for the trinomial, make sure you also square the 3 to get 9x squared. In the middle, we multiply these. 3x times y, I would just write that as the product, 3xy. And then at the end, plus y squared. If at any point you're feeling really confident with this technique, go ahead and hit pause and try them on your own. So let's go ahead and take a look at the next one, number 3, 27a to the third minus 8. So the way this one will work is we're going to take the cube root of each to get the binomial to start. That should be 3a minus 2. From there, we're going to square that first one, kind of like what we had in the last case. That's going to become 9a squared here. The only thing I'll tell you about this next step is if you can multiply these and write it as a simpler product than just writing in the middle 3a times 2. Here, the simplest way I could write that was 3xy. But 3a times 2 is the same thing as 6a. So, don't leave any work for me to do as the teacher if I'm grading your work. I want you to write 6a in the middle, not just that it's 3a times 2. And at the end, it's going to be plus 4, because if you square the second term of the binomial, that becomes plus 4. It does get a little bit more challenging when the powers get higher than something that's being cubed. But anything that's divisible by 3 is going to be a perfect cube. In fact, if you divide the powers by 3, that's how we're going to wind up figuring out what the cube root of each of these is. Okay, so for the cube root of x to the 6, it's going to be x squared. And then it'll be minus y cubed to start there. And think about it, if you multiply x squared times itself 3 times, x squared, x squared, x squared, you're going to get back to x to the 6th. But I would say students do commonly make minor errors when it comes to these larger exponents. From there, we got to square x squared to get x to the 4th, plus in the middle, we multiply. I'm just going to leave it as x squared y cubed in the middle. And then at the end, square the y cubed to get y to the 6th. So you'll see questions come up like that in other practice situations with larger exponents. So just beware for something like that. All right, we have one more thing that we have to talk about today, and it's the concept of what about the sum of perfect cubes? So if we're thinking about perfect squares and comparing the two processes, there's no such thing as the sum of perfect squares. There's a difference of perfect squares technique, but not a sum technique. There is a process for the sum of perfect cubes, however. It's really the same idea. The way you develop the binomial and trinomial are very similar. It's really just the signs that go in the middle of the binomial and trinomial that are different. So here's the general rule for the sum x cubed plus y cubed. It would factor into x plus y, and then the trinomial would be x squared minus xy plus y squared. So take a second, make sure you get that down correctly in your notes. It should look really similar to what we had for the difference. It's really just a few signs that are different. A good way to remember the signs is that depending on what this symbol is here, so in this case, we're doing the sum of perfect cubes, and the binomial will always keep the sign as the original expression. So if it's plus, it's plus. If it's minus, it's minus. The middle of the trinomial, you'll change that sign always. And then at the end, you're always adding no matter what. So if you compare this to the last technique of difference of perfect cubes, this idea of keep, change, add will apply for that technique as well. So if that helps you to kind of break down how to do the signs, that's something that we can kind of make simple mistakes with, but it's not a huge deal. All right, if you got down that rule, let's try some factoring with some sum of perfect cubes. Like I was saying, the way you break down the trinomial and the binomial, very much the same as what we were doing with the difference of perfect cubes. For x cubed plus 27, the binomial would be x plus 3, cube root of each of these. And then finally, the trinomial would be x squared minus the product 3x in the middle. Don't write that as x3. That wouldn't really look correct in standard form. And then finally at the end, plus 9. So hopefully it has a very similar feel. You know, we squared these terms to go in the front and end, multiply for the middle. 8a cubed plus 1 is going to be 2a plus 1 to start. And then from there, you would have 4a squared minus 2a in the middle, and then a plus 1 at the end. Challenge yourself and see if you can try number 3 as that y to the 6th term. So see if you remember how to work with that from the difference of cubes examples. I'm going to write down what the factorization is here. So 125, that was that 5x, right? Perfect. 5 to the third would be 125. It's going to become plus y squared. And then from there, you would have 25x squared for the first term of the trinomial. Just don't forget to always square that coefficient as well. Minus 5xy squared. And then at the end, plus y to the fourth. Okay, if you did well with that, you're definitely on your way. The last thing I'm going to do, I know it looks like it's the end of the notes, but I feel like I want to throw in one more bonus problem because I think it's a good one. How about a plus b cubed minus 64? When you're working with something like this, we saw on day one that maybe that dummy variable technique might be nice just to kind of get yourself established here. You can let x equal the quantity a plus b. So this looks a lot easier for me to factor than looking at the original. And I certainly don't want you to multiply this out 3 times because that's going to get really messy there. So if I make this x cubed minus 64, 4 cubed is 64, so it's x minus 4 times x squared plus 4x, and then plus 16. I'm going back to that pattern for the difference of perfect cubes. The last thing you have to remember is really just don't forget, replace that quantity a plus b. So it's going to be a plus b minus 4. The only thing you have to be cautious about when you plug in a plus b in the trinomial, it's the quantity a plus b squared. That is definitely not the same as a squared plus b squared. So be cautious about that. Plus 4 times the quantity a plus b. Could you distribute that 4 in? I guess. I'm not going to make you do that. So I think this looks probably is the cleanest looking version of what your final answer should look like. If you expand this and distribute, that would also be an equivalent answer. So we can definitely extend cubes a little bit further than probably what you would have seen in Algebra 2 last year, but that's it for today. And we'll be working on some more practice with cubes, and we'll have some homework on it next time I see you. Have a good one, guys.